let's start off with some Newton's method, because Newton's method is kind of cool. So I will first of all point out that Newton's method is maybe less useful than it used to be, right? It's typically used for estimating a root of a function or x-intercept of a function. And certainly with calculators, it's much easier to do so without Newton's method, but it's still a process that's worth knowing. So let's say we want to use Newton's method to say estimate the, sure, let's do square root of 3. Welcome, thanks. So sometimes this type of Newton's method question gets phrased as estimate some sort of irrational number using Newton's method. Another way of phrasing, which we'll work on in a minute, is estimate the root of this function or the x-intercept of this function where you're given a function. So here, before we can do anything else, what we need to do is think about what is this irrational number, the square root of 3, what is it a root of or a solution to? Well, root 3 is a solution to, it's going to look kind of lame at first, x equal to the square root of 3. We're not done, but that's where I would always start. So if you're trying to estimate something, write x equal to it. And then we want to try and write this as a polynomial, or we want to manipulate this so we can write it as a polynomial with integer coefficients. So if you were trying to maybe make this look nicer and not have any square roots in it, what could we do to both sides? Yeah, I'm going to close that door because I can't hear very well. This is going to be x squared equal to 3. And the only other thing I would do is subtract 3. So in estimating x equal to the square root of 3, what we're trying to do is we're trying to estimate the roots of x squared minus 3 equal to 0. So we're trying to do that. And oh, yeah, of course. Yeah, sure. I can post these on Sniff again. Sorry, 1 second. Now I couldn't for the life of me actually remember Newton's method, like the actual formula for it, because it just doesn't stick in my head. So let's see here. So here's the process. Let's draw everything. Let's draw 1, 2, 3. And I know that the square root of 3 is about like 1.7-ish, like 1.73. So that's going to hit right about there. So I've got something that looks like this. There's my parabola. It's coming up like this. It's going to hit right about there. So we're trying to estimate that value right there. And what we're going to do is we're going to start by guessing something that's close to it. I'm going to guess 2. So first guess. Let's see here. Yeah. X1 equal to 2. Now, that's not going to be right. Newton's method is an iterative process, meaning we're going to make a guess, and then each subsequent guess is going to get closer to the actual value. So here's the process. And I know this isn't like, you can totally do this by just memorizing a formula, right? But I actually want you to see kind of what's going on. So the whole idea is, well, here's what we're going to do. And yeah, my picture's all right here. There's 2. We're going to plug in 2. We're going to find the point on the curve, which would be 2, 1. And then we're going to find the tangent line through that point. My picture maybe doesn't show it very well, so let me kind of blow this up a little bit. If we're looking over here, here's 1, here's 2, and here's my, right, I'm looking like that. If there's my point, And here's my tangent line. Right, my tangent line, where it intersects the x-axis, that's going to be my new better guess. So that's the whole idea, is we're going to find that point, we're going to find the tangent line through it, and the new x-intercept, that's going to be our guess. So how do we actually do that? Well, because I always have to kind of work it out. So I'm going to say, I want the equation of this line. So I want y, so I want y minus y1 equal to the slope times x minus x1. This point here is my x1, y1, which in this particular case is 2, 1. The slope there, my slope is going to be f prime of x1, which in this case is f prime of 1, which is going to be, well, the derivative, the function is x squared minus 3. So f prime of x is going to be 2x. So f prime of 1 is going to be 2. So here's what I've got. I've got y minus 1. Sorry, y minus 1 equal to my slope times x minus 2. What am I trying to find? I'm trying to find this new point here. So I'm essentially saying this is my x1, y1, and this point here is my x, y. I'm trying to solve for x. What's y at that point right there? Yeah, it's totally 0. So we're going to say, okay, y is 0. And we're going to solve for x. So I'm going to divide both sides by 2. So I'm going to have -1 divided by 2 equal to x minus 2. And then I'm going to add 2 to both sides so that x is equal to 2 minus 1/2. And I feel like I don't think I made an error here. My picture definitely looks like I made an error. Not that I made an error, or maybe I just drew my picture not very well. Like maybe this isn't really quite so steep here. Maybe it goes back further, but I feel like that's not right. So let me double check here. And we've got that y minus y1 equals. All right, we set that equal to 0. Sorry, I'm just double checking now because I want to make sure this is right. We get minus f of x. Sure. Yeah. It seems, I guess, I'm just a little, so anyway, let's go ahead and derive the formula and we'll come back and see if maybe I made a mistake somewhere. So that's kind of the whole, so that's the idea, is that you're taking this guess, you're plugging it into the function, and you're finding the tangent line that gets you a closer guess. I feel like my closer guess should be on the right side of this point, not on the left side of that point, but maybe I've just drawn a bad picture. So here's the more general idea. We have y minus y1 equal to your slope times x minus x1. What we're going to do is we're going to replace things with what they're called. So we're trying to say that this is your f of x minus your f of x1 equal to your slope, which is going to be the derivative at your point x1 times x minus x1. And then I'm going to isolate my f of x here. So f of x is equal to f of x1 plus f prime of x1 times x minus x1. Just to kind of reiterate here, we're saying we know what the point x1, y1 is, or x1 comma f of x1, and we're trying to figure out what this new point x comma 0 is. So we're going to set y equal to f of x equal to 0. That's going to give us that point that's on the x-axis. doing that, we get 0 equal to f of x1 plus f prime of x1 times x minus x1. And we're going to solve for x because that's what we're trying to find. So let's see what we get. I'm going to subtract f of x1 from both sides. I'm going to divide both sides by f prime of x1. So negative f of x1 divided by f prime of x1 equals x minus x1. And then solving for x, I get x equal to x1 minus f of x1 over f prime of x1. And that's how we find the next point, which you typically call x2. So the next point in the iterative process is the previous point minus the function evaluated at that point divided by the derivative evaluated at that point. Or more generally, x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. And now I really want to double check my work to make sure that what I did in the first place was right. So if we look back at our first example, our function was x squared minus 3. Our first guess was, oh, I see the mistake I made. Our first guess was x1 equal to 2. And when I found the derivative, I wasn't being careful. My derivative shouldn't have been 2. My derivative should have been 4. So my derivative was 2x, but I plugged in x equal to 1 to find the derivative instead of plugging x equal to 2. So if you look back here for a second, I said my derivative there was f prime of x1, which should have been f prime of 2, which should have been equal to 4. So I should have had a 4 as my slope. And then when I calculated this, I would have ended up getting x minus 2 equal to negative 1/4 instead of negative 1/2. And then this would have been 2 minus 1/4, which would have been 1.75. Which seems like it's still on the right side of that answer there. So that's comforting to me. But we can just, so the bigger picture is, or maybe the smaller picture is, you're not going to derive this formula every time you do it. Right? You're just going to either memorize the formula if you have to, or not memorize it and be given it if you're given it. But if we actually take this example and start throwing this expression here, if our x sub 1 is 2, then our x sub 2 is going to be x sub 1 minus f of x sub 1 over f prime of x sub 1, which is 2 minus f of 2, which was 1 over f prime of 2, which is 4, which is 1.75, or if you prefer, 7/4. And then we would do it again. We would do it as many times as they asked us to. Typically, with these Newton's method problems, you're only doing a couple iterations, at least on if it's on an exam and you're not allowed to use a calculator, it really kind of gets tedious calculation-wise pretty fast. For example, if I wanted to find the next iteration, so my x sub 2 is 7/4, x sub 3 is going to be 7/4 minus f of 7/4 over f prime of 7/4. That's getting pretty ugly. It's going to be 7/4. F of 7/4 is 7/4 squared minus 3. So that's 49/16. Right, that's 7/4 squared minus 3, which is 48/16, all over f prime of 7/4. F prime of x is 2x, so that's going to be 2 times 7/4, which is 7/2. Yeah, it's getting pretty gnarly, right? That's a lot of calculation by hand. And you might say, well, at this point, I would pull out a calculator, and I would agree with you. But if you're pulling out a calculator, why wouldn't you just use the calculator to estimate the square root in the first place? So I hope I get the point of this is like understanding the process, but it also feels a little silly that at some point, totally, we could calculate this by hand. That's going to be 7/4 minus 1/16 times 2/7, which is something that's gross, and I don't really want to simplify that. And then you can do it again and again and again. Let's look at one more example, maybe two more examples. But what I will point out is whatever this is, it's going to be even closer to the square root of 3. So let's look at another example. It may be a slightly more useful example. So let's say we want to use Newton's method to estimate. Let's see what we got here. Yeah, we want to estimate the solution. Don't worry, after these couple examples, we'll get to more of Lupital's rule. Unless you don't want it. We want to estimate the solution to x cubed plus x squared minus 6 equal to 0. Ooh, that looks a lot of folks there. Okay. So first of all, does this even have a solution? Does x cubed plus x squared minus 6 equal to 0 have to have a solution? Well, there's a couple ways to say yes. One way is we know that an odd degree polynomial always crosses the x-axis because it has to go from low to high, from high to low. Even degree ones don't. Like if you got x squared plus 3, that never crosses the x-axis. An odd degree, certainly. We'd like to have a decent guess, though, of what the actual solution might be, because you don't want to start way away from your actual possible solution if you're trying to use Newton's method. So we can say that by the intermediate value theorem, there is a solution between x equal to -1 and x equal to +2, because f of -1 is -1 plus 1 minus 6, which is equal to -6, and f of +2 is 8 plus 4 minus 6, which is +6. Since the function is continuous and goes from a negative number to a positive number, it has to go through 0. So by the intermediate value theorem, there is a solution between these two things. So what do we want to start off by guessing? Well, let's take a look here. We know that f of -1 gave us -6. And f of 2 gave us +6. And somewhere between these numbers here, interesting. Sorry, I'm just looking at something real quick here. Oh, sure. So it's doing something like this. I don't really know. We got something like that. And there's our potential solution. I might try and narrow that down a little bit. Like I might also look at f of 0 is also -6, and f of 1 is 1 plus 1 minus 6, which is -4. So between 1 and 2, I have a solution. It's going from -4 to +6. I would probably pick, usually they're going to tell you what the first guess is, to be perfectly honest. But if I didn't have an intuition, I would probably guess the thing that seemed like it might be closer. I would probably guess x equal to 1 as my first guess. So we're going to start with x1 equal to 1. And then we're just going to jam this into the equation, meaning use x of n plus 1 equal to x of n minus f of x of n over f prime of x of n. That's it. So plugging in x of 1 equal to 1, we know that f of 1 is going to be 1 plus 1 minus 6. F prime of 1, well, let's write down what the derivative is. F prime of x is 3x squared plus 2x. So f prime of 1 is going to be 3 plus 2. So our next guess is going to be x sub 2 equal to 1 minus f of 1, which is -4 over f prime of 1, which is 5. So that's going to be 1 plus 4/5, which is 9/5. So we started here, we got this guess, and now what we're doing is we're drawing the tangent line. And we're saying, there's our next guess, which is 9/5. And then we're going to go up to the graph here and say, okay, there's our new guess, or here's our new guess. Go to the graph and then draw the tangent line, and that's going to be our next guess. And we're zeroing in on the actual value. So if we want to find x sub 3, it's going to be x sub 2 minus f of x sub 2 over f prime of x sub 2. And again, this is where things start to get kind of ugly, right? X sub 2 is 9/5. It's going to be 9/5 minus f of 9/5 over f prime of 9/5. I don't want to do 9/5 cubed. That seems terrible. Yeah, it's going to be, so this is where I would pull out a calculator, like, okay, this is going to be approximately, welcome on in. We're talking about Newton's method. So this is going to be approximately 1.569. And then you can plug that back into a calculator and say, okay, x4 is going to be x3 minus f of x3 over f prime of x3, which is going to be approximately 1.569 minus f of 1.569 over f prime of 1.569, which is about 1.534. So if I was actually doing these calculations, I wouldn't do them, and I wouldn't actually put them into a calculator. Here's probably, let me show you what I think is maybe the easiest way to handle this efficiently. So let me show you. I think this is kind of neat. So I'm trying to calculate this thing here, value minus f of that value over f prime of that value. So I'm actually going to graph that, meaning I'm going to, oops, come back up. I'm going to plug in y equal to x minus, so my f of x was x cubed plus x squared. Whoops, calm down there. Minus 6. And my derivative was 3x squared plus 2x. And now I'm actually going to plug in my first, so my first guess was what? It was 1, right? So let me grab a little table here. And now I'm going to plug in 1. Oh, come on. Really? Oh, you always do this. I don't want that. I did that wrong. You don't grab the table from here, grab the table from here, like that. So then if I start with 1, look, my next value is 1.8, like we got, right? When I plugged in 1, I got 1.8. And if I plug in 1.8 here, I get the next value. And I can take that value. Can I copy you? I cannot, but I can write it out, right? 1.569, etc. And you can keep doing it. So that seems like a pretty efficient way of getting to the next one, right? If you actually take your expression for x minus f of x over f prime of x and plug and start with your, in fact, we can delete these here, right? Start with your, whoops, holy smokes. Getting ahead of yourself there, James. Sorry about that. There we go. So if you start with your first value and then get your next value, you can keep just plugging that next thing in. I feel like there should be a way to copy this. Nope, I guess not. I really just want me to do that. Okay, no, that's not what I wanted. This doesn't like Control V, Control C apparently. Okay, so how do you foresee profs to make tests around Newton's method if we're not going to be able to use calculators? Right, so typically if someone's asking you a Newton's method question on a test, they're giving you a relatively easy function to deal with and they're asking you to do like 2, maybe 3 iterations at the most. This problem, so this problem, we can say that, or one way you can ask this sort of question on a knock test would be, do Newton's method enough times so that your estimate is accurate within like 2 decimal places. And so if we look here, we've got answers that are not the same to 2 decimal places, so we keep going. So if I plug in what 1.53819, my next answer is 1.537, and those are close enough, right? The first 2 decimal places didn't change, so that answer is accurate to within 2 decimal places. So 1.53 is an approximate solution of my original function, or my original equation, x cubed plus x squared minus 6 equals 0. So our solution is approximately 1.53. It's kind of interesting. It's kind of a giant pain in the butt, but such is math, right? Sometimes it's kind of a giant pain in the butt. The last thing I'll say about Newton's method. So this is probably what you'll have to do. If you have to do something, you'll probably have to do something like this, where you have to use the formula. They might give it to you, they might not. And then you have to just keep tossing in numbers until you've done enough. And enough is probably gonna be like, they're gonna tell you to do it this many times. I've always had trouble remembering this formula. Here it is. The next one is the previous one minus the function divided by the derivative. How did I know answers between -1 and 2? Good question. I actually wanted to be a little more precise about my interval. So here's what I really was doing. So I have x cubed plus x squared minus 6 equal to 0. And I'm thinking of this as my function. I'm really just going to start if they don't give me an interval, I'm going to start testing values until I get something where it's positive, something where it's negative. So I would have checked f of 0 and gotten -6. And then I would have done f of 1 and gotten 1 plus 1 minus 6, which is -4. And then I would have done f of, or I'm just going to keep using integers until I get something bigger. Oh, sorry, thank you. And I would have done f of 2 and gotten 8 plus 4 minus 6, which is 6. And so between 1 and 2, there's a solution by the intermediate value theorem. Because the function is continuous. So -1 and 2 actually wasn't the best interval to pick. +1 and 2 is a much better interval. Thank you. And then to choose a starting place, if they don't give you one, again, typically you're given where to start. But if I wasn't given one, I would pick the value of x that has the y value that's the closest to 0. So that's why I picked x1 equal to 1, because of the 2 where you go from negative to positive, this value has the y value that's a little closer to 0 than this y value. That's kind of it. That's really, it's kind of just this process where you're like, okay, I'm just going to keep plugging things into this iteration until I get whatever they're asking me for. And then again, right, here's the formula. It can be derived. It's kind of a pain to derive, but it's not terrible. The only other thing I want to point out is that Newton's method can fail. So you can have a couple different possibilities. For example, if your graph looked like this, and there was a horizontal tangent right there. And if that was our first guess, well, then you're going to get problems, because if that's your first guess, then the derivative is 0. And your second guess is going to be x1 minus f of x1 over f prime of x1. Oh, that's a problem, because that's going to be 0. Also, just graphically, right, the whole idea is that you plug in your first point, and then you follow the tangent line back to the x-axis. The tangent line's not getting us back to the x-axis. Whereas in the previous examples, right, when this was our first guess here, right, our first guess was 1, we went to the function, we followed the tangent line back to the x-axis, and that was our next guess. That doesn't work if you have a horizontal tangent line. A couple other ways this can fail is if you have something like, I'm just going to use the function. F of x equal to the cube root of x. Now I should point out, we all know what the root is here. The root is 0. But if you have something that was shaped like this and you were guessing, well, let's say we want to guess x equal to 1. So we're going to start here. We're going to go up to the function. We're going to draw a tangent line. We're going to end up somewhere over here. And then we're going to go down to the function. And we're going to draw a tangent line. And we're going to end up, you might end up back at the point you were, you might end up further away. But this is either putting us in a loop or in an outwardly going spiral where we're actually not getting closer and closer to the solution. If we actually use the formula, so x2 is going to be x1 minus f of x1 over f prime of x1. That's going to be, let's see, like I'm making a mistake here. No, I should write what f prime of x1 is though. Prime of x is 1/3 x to the negative 2/3. So f of 1 is going to be 1, and f prime of 1 is going to be 1/3, and that's going to be a problem. So we're going to end up way over here at negative 2. We're going to plug that in, and then we're going to end up even further out this way. So sometimes we can spiral outwards. Or you can end up in a loop, right, where you keep going around and around and around in the same values. Just to illustrate that Newton's method doesn't always work. Again, I don't really see this being a possible test question, but if we're talking about Newton's method, I should point out, yeah, there are some ways it doesn't work. The original question, yeah, so the original question was between -1 and 2, but that's because I kind of botched it. A better original interval would have been between +1 and 2. And the problem is if you start too far away from your answer, you might not get it to work. You could have something, for example, if I have a function that looks like this, and I'm trying to estimate this root right here, if I start somewhere over here, I'm going to be in trouble. Because if I start there and I draw the tangent line, and the tangent line is getting me way over here, and that's my next guess. That doesn't seem good. So your guess needs to be close enough to your actual value that when you like if my guess is say like here, when you plug in the point, the function, and then draw the tangent line, your tangent line is getting you a value that's somewhat close to where you want to be. How do you get 1/3 when I plugged in 1? Sure. So the way I got 1/3 was my derivative was f prime of x equal to 1/3 x to the negative 2/3. And when you plug in 1 for x, you get 1/3 times 1 to any power is 1. Right. The question is asking for estimate values between 1 and 2. And we can just say IVT says there are values between the two x values. Why would there need? So there's two different questions. One question could be, show there's a solution. And if you're just showing there's a solution, intermediate value theorem is sufficient. You say, oh, there's a solution between 1 and 2. What Newton's method for is for estimating the solution. So we're trying to get a better and better estimate of the answer. So for this question where we were talking about x cubed plus x squared minus 6 equal to 0, we can say there is a solution by the intermediate value theorem. And then we can say via Newton's method, the solution is approximately 1.53, at least to 2 decimal places. So that's the point of Newton's method, not to show there's a solution, but to approximate the solution. Other questions about Newton's method before we move on? It's kind of interesting. I will again say it is something that some classes do just skip. So if your class isn't talking about it, that's perfectly fine. It's kind of what even in like the syllabus for 21A, it says on it like you can skip this section if you're running low on time. So if your teacher has decided to skip it, I would say don't sweat it. I don't think it doesn't really ever come up in future classes. I'm trying to think. No, I mean Newton's method, I can't think of a time when it's come up in 21B or 21C. Oh, can I use my fingers? Newton's fingers. All right, so I'm happy to address other questions on Newton's method if you have them, or if you think of something later, don't hesitate to ask it. Well, let's go ahead and circle back around to L'Hopital's rules. So last class, which was a whole week ago, we talked about L'Hopital's rule a little bit, and we mostly just covered the main, well, I mean, the two main ways of using L'Hopital's rule, which is if you have an infinity over infinity or 0 over 0. In fact, these are actually the only times you can use L'Hopital's rule. If you have anything else and you want to use L'Hopital's rule, you have to make it look like this to use L'Hopital's rule. So these are the only forms where we can just straight up use L'Hopital's rule. These other indeterminate forms, you have to do some work before you can use L'Hopital's rule. So L'Hopital's rule is only applicable for the limit of a 0 over 0 or infinity over infinity type. But I do want to make you all aware that each of these things are what's called an indeterminate form. Infinity minus infinity, 0 times infinity, 0 to the 0, infinity to the 0, and 1 to the infinity. Now, I should point out, when we say something like 0 times infinity, we don't really mean 0 times infinity. We mean a really small number times a really big number. So an example of that, which I'll show in a second here, would be the limit as x goes to 0 from the right of x times the natural log of x. This isn't really 0 times infinity. It's just a very small number times a very negatively large number. If x is going to 0, well, x is going to 0. And the natural log of x, if x is getting closer and closer to 0, the natural log of x has that vertical asymptote, and the function gets negatively really large. The reason I mention this is because 0 times a number would be 0. But this is just a really small number times a really large number. It could be really small. It could be really large. It could be somewhere in between. But it's definitely not always 0. And that's why we call things indeterminate forms in general, because they're never one thing, right? If 0 times infinity was always 0, we would just say it's 0. We wouldn't say it's indeterminate. But it's not always 0. This one is going to be 0, though. So if I was going to do this one, I would need to rewrite it as a fraction. So I'm going to write this as the limit as x goes to 0 from the right of the natural log of x divided by the reciprocal of x. Because I want these still to be the same. So multiplying by x is the same as dividing by 1 over x. And now this is an infinity over infinity form. Technically, it's a negative infinity over infinity. I don't really care about the signs of my infinities when I'm doing this part, because I just need it to be some sort of infinity over some sort of infinity. But it's good to be aware if it's positive or negative. Now we can use L'Hopital's rule, right? We've got the right thing. We can apply the rule. So we're going to do L'Hopital. It's going to be the limit as x goes to 0 from the right. The derivative of the natural log of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. I would encourage you all to get comfortable with knowing that the derivative of 1 over x is negative 1 over x squared. I know we can totally rewrite it, right? 1 over x is x to the minus 1, and the derivative of x to the minus 1 is minus x to the minus 2. But it's going to be nice just to go straight from, oh, the derivative of 1 over x is negative 1 over x squared. Because then you don't have to like rewrite it and then rewrite it again, because I want it to look like this so I can simplify this easily. At this stage, I could use L'Hopital's rule again. In fact, what I should really say is, after you use L'Hopital's rule, we should try and evaluate the limits. If I plug in 0 for x, what do I get? Well, if I don't simplify it, I get infinity on the top and negative infinity on the bottom, which would seem to indicate I should use L'Hopital's rule again. Before you use L'Hopital's rule another time, you should simplify your expression. So simplifying this, I get the limit as x goes to 0 from the right of 1 over x times x squared over negative 1. And then I can cancel an x. That's the limit as x goes to 0 from the right of x over negative 1, or just negative x. And now we can see, oh, we don't actually need or are able to use L'Hopital's rule. This no longer is an infinity over infinity or 0 over 0 type of thing. This is just 0 when I plug in 0. So if you have an indeterminate form that's not infinity over infinity or 0 over 0, we want to make it so it is. Then we want to use L'Hopital's rule. And immediately after using L'Hopital's rule, you should always check to see, can you plug it in? Either you can, and great, you've got something, or you think you can't, and you've got L'Hopital's rule again. So then you try and simplify, and then you double check to make sure you can plug it in. Let's look at lots more examples. Also, stop me if you have, I feel like I don't need to say it. I keep saying it because it's just a natural thing to say. If you have questions, of course, ask them, right? Always. If you have questions, ask them. All right, so let's look at this one, which this definitely is an infinity minus infinity type of limit. This is going to infinity. This is going to infinity. I've got a 1 over 0 and a 1 over 0. Now this is here, when you have a specifically infinity minus infinity, you do have to pay attention to the signs. Because if you had infinity minus negative infinity, that would just be infinity, right? Infinity plus infinity is infinity. Or if you had negative infinity minus infinity, that would be negative infinity. But if you have infinity minus infinity, who knows, right? They might be the same, they might be slightly different, one might be way bigger than the other. You could get literally anything. So when you're subtracting fractions, the only way to subtract fractions is to get a common denominator. So I'm going to rewrite this as the limit as x goes to 1 from the right. I'm going to multiply this by natural log of x over natural log of x. So natural log of x over natural log of x times x minus 1. Minus, I'm going to multiply this by x minus 1 over x minus 1. And now that I have a common denominator, I can actually put them together. So I'm going to write this as the limit as x goes to 1 from the right of the natural log of x minus 1 over the natural log of x times x minus 1. And then I'm going to check now I should be able to use L'Hopital's rule, because if you have something that's an indeterminate form, once you've simplified it into a fraction, it should end up being a 0 over 0 or infinity over infinity. If I plug in 1, on the bottom, I definitely have 0, right? Natural log of 1 is 0 and 1 minus 1 is 0. So I got 0 times 0. If I plug in 1 on the top, did I get 0? I don't. What am I getting? I'm getting negative 2. Natural log of 1 is 0, minus 1 is negative 2. Right, exactly. So the whole point here is that you should be getting something where you can use L'Hopital's rule. So if you're not getting a 0 over 0 or infinity over infinity, you should go back and check, did I make a mistake? And I did make a mistake, right? This minus x minus 1 should be a minus x plus 1. That minus sign should distribute there. But if you see, so right, exactly, it should be plus 1. So if you see that you are getting something, that's why it's important you should check, right? Because maybe you're like, oh, well, I know it should work, so I'm just going to go ahead and use it. And it actually probably wouldn't make a difference here, because the plus 1, the minus 1, when you take the derivative, isn't going to matter. But it's still important to get it right. So when you do this, you definitely want to be like, well, do I actually have 0 over 0 before I use L'Hopital's rule? Or do I actually have infinity over infinity? It's always something you should get in the habit of checking. Don't just throw L'Hopital's rule at something until after you're sure you can use it. Because sometimes teachers like to ask questions where you can't. Like they're like, I'm going to give them something that looks like it could be kind of like 0 over 0, but it's really not. So just be extra careful. So now we're going to use L'Hopital's rule. It's still a limit, right? L'Hopital's rule is only for limits. The derivative of the top is 1 over x minus 1 plus 0. The derivative of the bottom is, I guess I'm going to use the product rule. It's 1 over x times x minus 1 plus natural log of x times 1. And if we plug in 1 at this point, I'm still getting 0 over 0. So I'm going to do it again. And before I do it again, I might do some simplifying. I'm going to run out of room here. So if the limit as x goes to 1 from the right of 1 over x minus 1, I'm going to distribute this 1 over x here to get 1 minus 1 over x plus the natural log of x. And you might consider multiplying the top and bottom by x. I don't think I would here though, because that would give me an x times natural log of x. I feel like I'm making things more complicated than less. Correct, yeah, I said be extra careful and don't accidentally apply L'Hopital's rule to functions to limits that don't need it or that can't have it. And we'll see some examples of that a little bit later. Here I can use L'Hopital's rule again because I still have a 0 over 0 type. So I'm going to take the limit as x goes to 1 from the right. The derivative of 1 over x is negative 1 over x squared. The derivative of 1 is 0. The derivative of negative 1 over x is positive 1 over x squared. And the derivative of the natural log of x is 1 over x. And now we can plug in 1 and get negative 1 over 1 over 0 plus 1, which is negative 1/2. So here, infinity minus infinity is negative 1/2. Kind of bizarre, right? This infinity is just a little bit larger than that infinity, which I know, again, seems strange to say, but that's what's really going on here. If you look at the graphs of these as x approaches 1, they're very close to each other, but they always kind of differ by just a little bit. Kind of cool. Let's look at another example. Okay, let's look at following. So most of the time, I don't know, most of the time, the other, no, we should do more like that, sorry. Let's look at this one. Limit as x goes to infinity of x squared times e to the negative x. And this is definitely an infinity times 0. So x squared is going to infinity, e to the negative x is going to 0. Okay, so I need to rewrite this. I need to rewrite it as a fraction. There are two ways to go. Usually one way is always better than the other. Meaning you could go this way and say its limit as x goes to infinity of e to the negative x divided by x to the minus 2. Or you could go this way and say its limit as x goes to infinity of x squared over e to the positive x. Which of these is better? The question really is, which one is eventually going to have things work if you keep applying L'Hopital's rule? This one here is an infinity over infinity. This one over here is a 0 over 0. They're both perfectly fine as far as L'Hopital's rule is concerned. But here's the difference. This top one, if you apply L'Hopital's rule, let's see what happens. So I'm going to get the derivative of e to the negative x, which is negative e to the negative x. And the derivative of x to the negative second is negative 2x to the negative third. This didn't really get better. I still have something that's going to 0 on top and something that's going to 0 on the bottom. I find this harder to see. Like if I was thinking about this, I might actually think of it as negative 1 over e to the x over negative 2 over x cubed. So be like, oh yeah, x is going to infinity, so I've got a 0 on top, I've got a 0 on the bottom. But what's going to happen if we keep using L'Hopital's rule is that this denominator, the power is going to get more and more negative. I'm not going to get closer and closer to something that's going to actually have a limit that exists. On the other hand, writing it this way, when I use L'Hopital's rule once, I get the limit as x goes to infinity of 2x over e to the x. And then when I use L'Hopital's rule again, because it's still infinity over infinity, I get the limit as x goes to infinity of 2 over e to the x. And this is clearly the superior way of approaching this problem, because x to a positive power, when you keep taking the derivative, eventually the derivative of x to a positive power will become a constant term if you take enough derivatives. Our limit's going to be 0. You've got 2 over infinity. Let's look at another one. Something like the limit as x approaches 6 of 6 from the, do I have a side? Sure. 6 from the left, 6 minus x times tangent of pi x over 12. Feels a little convoluted. Well, let's take a look. So if I plug in 6, what do I get? Plugging in 6, I get 6 minus 6 times tangent of pi over 2. 6 minus 6 is 0. And what's tangent of pi over 2? Now, tangent of pi is 0 and tangent of 0 is 0. The tangent of pi over 2 is where you have a vertical asymptote. Tangent of pi over 2 is some sort of infinity. Specifically, if we're approaching 6 from the left, we're a little bit less than 6. When you plug in a little number a little less than 6, you're a little bit less than pi over 2. So you're actually the positive infinity. If you think about the graph of tangent, there's pi over 2, and pi over 2. I'll take that. So as the values of the angle approach pi over 2 from the left side of pi over 2, the values of tangent approach infinity. So now the question is, how do I make this so I can use L'Hopital's rule? Well, again, you always kind of have two options when you have a 0 times infinity. You can either bring the 0 part down in the reciprocal of it, or the infinity part down in the reciprocal of it. So you can either do this as the limit as x approaches 6 from the left of tangent of pi x over 12 divided by 1 over 6 minus x. Or you can do the limit as x approaches 6 from the left of 6 minus x over 1 over tangent of pi x over 12. And the question that usually kind of decides which way to go is, which denominator is easier to differentiate? Is it easier to differentiate 1 over 6 minus x? Or is it easier to differentiate 1 over tangent of pi x over 12? And it's not always clear. Without really thinking about it, you might say the first one's easier. It seems like 1 over 6 minus x seems less complicated than 1 over tangent of pi x over 12. Until you remember that 1 over tangent is cotangent. And so I can actually rewrite this as a limit as x approaches 6 from the left of 6 minus x over cotangent of pi x over 12. And then that seems like it's probably better. If we apply L'Hopital's rule here, let's see what we get. We have a limit as x approaches 6 of the derivative of the top is -1. The derivative of the bottom, 6 from the left, sorry. The derivative of cotangent of some stuff is negative cosecant squared of that stuff times the derivative of the inside stuff. The derivative of the inside stuff is just pi over 12 because it's the derivative of pi x over 12. Now, this certainly doesn't look like a limit where I could use L'Hopital's rule again, because I don't have a 0 or an infinity on the top. Maybe there's some rearranging I could do where I would need to use it, but before I should do any of that, I should just check, can I plug in 6 and get a real answer? So the question really is, what's cosecant of pi over 2? Is it, hopefully it's not 0, right? If it's 0, we're going to be feeling not good. Is cosecant of pi over 2 0? Or is it not? Cosecant of pi over 2 is the reciprocal of sine of pi over 2, and sine of pi over 2 is positive. This is definitely going to be -1 over -1 times pi over 12, which would be 12. So it is relatively important to make sure we know how to evaluate the trig functions at various angles, because they do come up in some of these Hopital rule questions. Let's take a short break so I can use the restroom and fill up my water. And then we'll come back and we'll talk about the exponential forms. So we'll talk about the 0 to the zeros and the 1 to the infinities and the infinity to the zeros, because all of those types of expressions where you have a limit of them require a specific kind of process for using what we tell tool. But yeah, let me go grab some water. Use the restroom. Grab it. You're all over. Welcome to the restroom. So let's look at some exponential indeterminate forms. Let's start with the following kind of standard example. We'll find the limit as x goes to 0 from the right of x to the x power. This is definitely a 0 to the 0 type of limit. And a lot of the time they end up being 1, but not all the time. So how do we deal with this? Well, we deal with these exponential ones where you have a variable in your exponent in a very similar way you would deal with taking the derivative of something exponential. You do it by using a natural log. And there's kind of two schools of thought. One way of doing this is to say, I'm going to do the limit as x goes to 0 from the right of e to the natural log of x to the x, and then just do that the whole way through. So in fact, I'm going to show both ways so that you guys can kind of see what I mean when I say both ways. So one way of doing this is to do it like this, and then I'm going to write this as, people like to write the limit in the exponent. So I'm going to write this as the limit as x goes to 0 from the right of e to the x times the natural log of x. But the whole reason of writing it this way, e to the natural log of x to the x, is so that you can bring down that x in front. And then I'm going to write this as the limit as x goes to 0 from the right of e to the natural log of x over 1 over x. Because now that exponent is in a form where we can apply L'Hopital's rule. Natural log of 0 goes to negative infinity, and 1 over 0 goes to positive infinity. So that is definitely an infinity over infinity form. Technically a negative infinity over infinity form. It doesn't really matter, but you can, and people do rewrite this as e to the limit as x goes to 0 from the right of the natural log of x over 1 over x. So we'll write exp, right? Exponential meaning e to the power of, that's also fine. But now we can use L'Hopital's rule. Here we're just using the fact that the limit of a function is like, if you have the limit of a function of something, it's equal to the function of the limit of the thing, as long as the function is continuous, which e to the whatever always is. So we're going to rewrite this as e to the, now we're going to write, or we're going to use L'Hopital's rule and say, well, limit as x goes to 0 from the right, I'm going to take the derivative of the natural log of x, which is 1 over x. The derivative of 1 over x is negative 1 over x squared. We're going to rewrite that as, oops, what did I forget? It's not a huge deal, but it's a big enough deal that we better write it. I forgot it twice. I have to write the limit. Limit is really important. We do need to write it every step until we actually find the value. So that's going to be the limit as x goes to 0 from the right of e to, oops, oh, nope, sorry. So I'm so used to writing the limit in front that I kind of like, I was like, I need to write the limit, but I had already written the limit, I just moved it. I apologize. I didn't forget it, I just got caught up. That doesn't need to be there, that doesn't need to be there. Sometimes you get overexcited about the limits. That's going to be e to the limit as x goes to 0 from the right. 1 over x divided by negative 1 over x squared simplifies as just negative x. Taking the limit of that, that's going to be e to the 0, which is 1. So that's how some people prefer to do it. They like to write it as e to the natural log of your thing, and then do all the work like that. Alternatively, here's what other people like to do. You can say, well, I'm going to look at the limit as x goes to 0 from the right of the natural log of x to the x. And then our answer will be e to that limit. It's still the same work. We're going to get e to the something, where the something we're about to find is the limit as x goes to 0 from the right of the natural log of x to the x. I think people like doing it this way more because it feels like you're writing less stuff. So doing it this way, we're still just saying, okay, I'm going to bring the x down, x times natural log of x. That's a 0 times a negative infinity. So then we're going to bring the x down as 1 over x. So I have the natural log of x over 1 over x. Now we can use L'Hopital's rule. The limit as x goes to 0 from the right of 1 over x over negative 1 over x squared. That's going to become the limit as x goes to 0 of negative x, which is 0. But our answer isn't 0. Our answer is e to the 0, which equals 1. So either way of doing it, it's fine. It's really the same word. It just depends on how you want to manage like what you're writing. I've kind of gone back and forth over the years. For a while, I was like, no, we should totally do it this way because you're kind of writing the same one the whole way. But then I was like, well, this is kind of nice because you don't have to write as much while you're doing it. Either way is fine. Your teacher probably doesn't care which way you do it. Obviously, if they do care, you should do it the way that they want you to do it. But it really shouldn't matter. Let's look at some more examples. And I'll probably go this way. I'll probably go back and forth actually. So let's try the limit. Try the limit as x goes to 0 of sine of 2x. Let's do sine of 3x to the x. And so we're going to look at the limit as x goes to 0 of the natural log of sine of 3x to the x. And then whatever our answer is going to be, whatever we get here, our actual answer is going to be e to the that. So when I'm doing it this way, I like to start off saying, okay, this is going to be e to whatever I actually get. So I don't forget that I need to do that at the end. So this limit's going to be the limit as x goes to 0. I'm going to bring down the x. And then we're going to bring it down below me, right? You can probably do that in one step, right? We do it so often where you bring down the power and then you make it its reciprocal. So I'm going to write this as the limit as x goes to 0 of the natural log of sine of 3x over 1 over x. No, that's fine. Sorry, I was just thinking about. I guess we should have checked to see that we could use L'Hopital's rule. This is a 0 to the 0 form. So if you have a 0 to the 0 form, you should be able to use L'Hopital's rule. And now looking at here, oh yeah, we definitely have a natural log of a 0, which is going to minus infinity, and a 1 over 0, which is going to infinity. I probably should have been more specific with my limit, and that it probably should be x approaching 0 from the right. The reason it needs to be coming from the right is because sine of a number that's a little bit larger than 0 is positive, and natural log of a positive number is fine. But if you were coming at 0 from the left, if you're a little bit negative, sine of a slightly negative number is a negative number, and you can't take the natural log of a negative number. So here we do need to be approaching from the right. Same thing was true in the previous problem, right? You need to be approaching 0 from the right, because if you approach 0 from the left, you're going to have natural log of a negative number, which is a problem. It's also true that negative numbers raised to negative powers get super weird. Like if you've ever graphed x to the x, or like graphed it on Desmos, it looks perfectly normal-ish to the right, and then it's very exponential looking, except more than exponential. But to the left, it kind of disappears. There's like points here and there, because you do like -1 to the -1 is fine, or -2 to the -2. It works fine for integers, but like -1/2 to the -1/2 power is a problem, because you're taking the reciprocal square root of a negative number, and that doesn't exist. So x to the x, when x is negative, we don't usually think about it. I should be using L'Hopital's rule here. So let's see, we're going to get the limit as x goes to 0 from the right. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, and the derivative of sine of 3x is cosine of 3x times 3 all over negative 1 over x squared. That's kind of gnarly. Yeah, it's really gnarly. So if I was doing this, I would do some rewriting, right? If I try plugging in 0 now, cosine of 0 is 1, sine of 0 is 0. So I have a 1 over 0, which is infinity. If I plug in 0 down here, I've got a 1 over 0, which is some sort of infinity as well. And seeing it's infinity over infinity, I could use L'Hopital's rule again, but before I do that, I should simplify my expression. So let's see what happens when we simplify this here. The limit as x goes to 0 from the right. I might write the top as 3 cotangent of 3x over negative 1 over x squared. And I might even write this as the limit as x goes to 0 from the right of negative 3x squared times cotangent of 3x. Now that might seem bad in that I've just kind of worked myself away from being able to use L'Hopital's rule again. I kind of wanted there to be a fraction. But I really don't love this fraction option. Because taking the derivative, so typically it's not a great idea to keep taking derivatives of x to negative powers. This negative 1 over x squared, or negative x to the negative second, its derivative is going to have a power that's more negative. It's not usually helpful. We're kind of moving, right? You want to be moving in a direction where the powers of x are becoming less if possible. So what my idea here really is to put the x squared on top and put the cotangent on the bottom. I'm actually going to write this as the limit as x goes to 0 from the right of negative 3x squared divided by, what's the reciprocal of cotangent? Tangent. And now that seems like it might not be terrible. It might still be terrible. Let's see what happens. The limit as x goes to 0 from the right. I can't, well, I actually should say, I can use L'Hopital's rule because tangent of 0 is 0 and negative 3 times 0 is definitely 0. So using L'Hopital's rule, the derivative of negative 3x squared is negative 6x. The derivative of tangent of 3x is secant squared of 3x times 3. Now I should check again. Can I plug in 0? Do I get 0 over 0? Well, I definitely get 0 on the top, but secant of 0 is 1. So I end up getting 0 over 1 times 3, or I guess negative 6 times 0, like 1 times 3. That's going to be 0. So my limit here is 1. Sorry, one second, I want to look. There's an example I did just the other day that I thought was really good. I want to grab it again. One moment. Okay. Smooth. Let's look at one more 0 to the 0 type, and then we will do some other ones. Let's say we want to do the limit. X goes to 0 from the right of sine of x to the 1 over natural log of x. Always good to think about, can you even use L'Hopital's rule? Well, obviously not here, right? We need to rewrite it. But first of all, is it 1 over 3 indeterminate exponential forms? Is it 1 to the infinity or infinity to the 0 or 0 to the 0? And it's definitely 0 to the 0. Sine is going to 0. Natural log is going to negative infinity, and 1 over negative infinity is going to 0. Sometimes I like to write what indeterminate form is in quotes like that. Because it's not really equal to 0 to the 0, but it's kind of what we're thinking about. So I'm going to look at the limit as x goes to 0 from the right of the natural log of sine of x to the 1 over natural log of x. And then the whole reason for doing that is I'm going to bring that down. It's going to be the limit as x goes to 0 from the right of 1 over natural log of x times sine of x. And I probably could have saved myself a step here if I just would have written that as the limit as x goes to 0 from the right of sine of x over the natural log of x. Right? There's no having to flip and multiply or flip and divide here because it's already kind of in the denominator. So let's use L'Hopital's rule. Actually, can we use L'Hopital's rule? Can we use L'Hopital's rule? Feels like we should be able to, but I feel like it's kind of funky. Sine's going to 0. Oh, I made a mistake. What did I do? From here, go ahead. Right, I lost the natural log on my sine function. So again, it's always good to check to make sure if you've started off with an indeterminate form that's 0 to the 0, or we'll see 1 to the infinity or infinity to the 0. After you've done the taking the natural log and simplifying things, it should be a fraction where you can use L'Hopital's rule. When I looked at that without the natural log there, oh, I was like, well, sine of 0 is 0, and natural log of 0 is negative infinity. I had a 0 over negative infinity, which is problematic, right? That's not something where I can use L'Hopital's rule. But what I really had was a natural log of 0, which is a negative infinity over negative infinity. So it's always good to check before you start using L'Hopital's rule. Now we're going to use it. We're going to get the limit as x goes to 0 from the right. The derivative of natural log of sine of x is 1 over sine of x times cosine of x. The derivative of natural log of x is 1 over x. And there's a couple ways you can tackle this one. I'm going to rewrite this as the limit as x goes to 0 from the right of x times cosine of x over sine of x. That's a perfectly fine way of writing it. You could also write it as the limit as x goes to 0 from the right of x over tangent of x. That would also be fine. Either way, I have a 0 over 0. Here I have 0 times 1 over 0. Here I have 0 over tangent of 0 is 0. I think the second way looks better, right? I don't want to use the product rule if I don't have to. So using the second expression and get the limit as x goes to 0 from the right. The derivative of x is 1. The derivative of tangent of x is secant squared of x. And that's going to give me 1 over 1, which is 1. Which is not my final answer. My final answer is that the limit as x goes to 0 from the right of sine of x to the 1 over natural log of x is e to the 1, which is just e. Questions about any of this? Questions from the Zoom folks? Questions from the people? I mean, it does get, the process does get to be kind of repetitive, right? You're like, okay, they do the same thing over and over again. And the only thing I can really say as we do more examples is just make sure you're careful, right? It's easy to lose a thing. It's easy to lose a natural log. Always check before you use L'Hopital's rule. Can I actually use L'Hopital's rule? Now, if you're taking a test and the person says use L'Hopital's rule to do this question, you probably don't need to check it. Just be careful what they bring, right? Sometimes they might write like, use L'Hopital's rule, or say why you can't use L'Hopital's rule to do this. So some teachers are more straightforward than others. Just be aware. All right. Why is it, excellent question. Why is it e to the whatever? So the thing is, our original question was to find the limit as x goes to 0 of sine of x to the 1 over natural log of x. But what we actually looked at was the limit as x goes to 0 of the natural log of sine of x to the 1 over natural log of x. So here's what's kind of really happening. This limit here that we wanted to find, that's equal to the limit as x goes to 0 from the right of e to the natural log of your stuff. Because e to the natural log of anything is just the anything, right? E to the natural log of stuff is just the stuff. So we found, definitely write it this way, this is the same as e2, the limit as x goes to 0 from the right of sine of x to the 1 over x. Sorry, the natural log of sine of x to the 1 over x. But we found that limit. That limit was what we did up here, right? And the limit as x goes to 0 of the natural log of sine of x to the 1 over x is 1. So that's 1, but our overall answer is e to the 1. And again, you have choices. You can either decide to do it like I've done it, where you look at the limit of the natural log of your expression, do all the work, get an answer, and then say that your actual answer is e to whatever that number is. Or you can write it all out at every step. So in fact, I'll do the next one the other way to kind of point it out. So let's look at a classic example. A lot of these are pretty classic. Let's look at the limit as x goes to infinity of 1 plus 1 over x to the x. And I will tell you that you might have to show this on a test. Eventually, you should memorize what this limit is, because this limit will come back in 21B or C for sure. And it might have already, it's probably already shown up in this class earlier, in fact. So we're going to do it the other way. I'm going to do this as the limit as x goes to infinity of e to the natural log of 1 plus 1 over x to the x. And we're going to rewrite this as e to the limit as x goes to infinity of, I'm going to bring the x down, so it's x times the natural log of 1 plus 1 over x. And finally, we want to get it into a form where we can use Lupital's rule. So it's going to be e to the limit as x goes to infinity of the natural log of 1 plus 1 over x over 1 over x. And now we can use L'Hopital's rule, because the denominator is going to 0 and the numerator is also going to 0 because it's a natural log of 1. I should also mention, just as an aside, this is a 1 to the infinity indeterminate form. The base is going to 1, the exponent is going to infinity. And I should also say 1 to the infinity is not going to be 1 necessarily, right? Because it's not 1 times 1 times 1 times 1 times 1 times 1 event all over and over again. It's a number that's a little bigger than 1 times itself, times itself, times itself, times itself. And eventually, you multiply it by itself enough times to kind of overcome the fact that it's so close to 1. So let's take a look here. We're going to use L'Hopital's rule. We're going to get e to the limit as x goes to infinity of the derivative of the natural log of some stuff. So the derivative of the natural log of stuff is 1 over the stuff. So 1 over 1 plus 1 over x times the derivative of the stuff. The derivative of 1 is 0. The derivative of 1 over x is negative 1 over x squared. And then the derivative of the bottom is also the derivative of 1 over x, which is negative 1 over x squared. And this kind of happens a lot, where you have the derivative of 1 over x in the top and the bottom, and they just totally cancel out. The negative 1 over x squared here cancels with the negative 1 over x squared here. Super nice. Happens a lot. This is going to be e to the limit as x goes to infinity of 1 over 1 plus 1 over x. The 1 over x goes to 0, and we're left with e to the 1, which is e. I'm not going to go through all the work for it, but I will just point out that if you had done this the other way, if you had done the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x, you would have done a bunch of work, and eventually you would have gotten the limit as x goes to infinity of 1 over 1 plus 1 over x, which would have been 1. And then your actual answer would be e to that limit. Which would be e to the 1, which is 1. Either way is fine. Do whatever you're more comfortable with, unless your professors like to do it in a specific way. Even then, I still might do it the way I was more comfortable with, because it's more important to be able to do it right than be able to do it the way they said to do it. So this is a pretty common limit to be aware of. The limit as x goes to infinity of 1 plus 1 over x to the x is equal to e. And usually, for all these 1 to the infinity type forms, the limit ends up being something to do with e, which again makes sense, right? Because all of them you're going to be doing e to the something. And you're either going to get e to a non-zero number, which has an e in it, or you're going to get e to the 0, which is 1. There's kind of not a lot of other options. So, time is okay. What if we wanted to do the limit as x goes to infinity of 1 minus 3 over x to the x power? So I wanted to show you two things. Thing one is, eventually you're going to want to be able to, like when you take 21C, you take 21C, you're going to want to be able to look at this limit and know that the answer is e to the negative third without actually having to do the work. I want to show you that really quickly, and then I'm going to show you the long way. But here's kind of how you see it in the short way. If you have the limit as x goes to infinity of 1 plus a thing or some stuff, and then raised to the reciprocal of that stuff. I should really say, if x is going to infinity, the stuff has to be going to 0. If this is the case, where you have 1 plus a thing to the 1 over that thing power, as long as these are exact reciprocals, and this one's going to 0, and that one's going to the reciprocal of 0, this limit's going to equal e. Which is definitely what we had in the previous example, right? In the previous example, we had 1 plus some stuff that was going to 0, and exactly raised to the power that's the reciprocal of that stuff. Those are exact reciprocals. So how can you use that fact to show that this is equal to e to the negative third without doing all the work? Well, we're still going to do all the work. But here's how you could do it. You can say, well, look, James, this is the limit as x goes to infinity of 1 minus 3 over x to the, I really like that power to be x over negative 3, to be the reciprocal of negative 3 over x. So I'm going to do that. But then I also need a multiple of negative 3 to undo it, which I know looks super funky. But now check this out. That's going to be the limit as x goes to infinity of 1 minus 3 over x to the negative x over 3, all to the negative third power. And then I'm going to bring the limit inside, meaning I'm going to write this as the limit as x goes to infinity of 1 minus 3 over x to the negative x over 3. Is that inside part equal to e? You bet it is, because you have a 1 to the infinity form, and it's exactly 1 plus a thing raised to the reciprocal of that thing's power. So those are reciprocals, and negative 3 over x is going to 0, and negative x over 3 is going to some sort of infinity. It doesn't matter if it's positive or negative. All right. So in the future, you can use this idea to be like, oh, this limit's just going to be e to the negative 3. That's not what we're going to do right now, but I kind of wanted to let you see that because it is something you will actually want to be able to do in the future. For now, we're going to do it the long way. And I'm going to do it the way where I just look at the natural log. So I'm going to look at the limit as x goes to infinity of the natural log of 1 minus 3 over x to the x. So here's what I'm expecting to happen. I'm expecting this limit to end up equaling negative 3, and then my actual answer will be e to the negative 3. So let's do this next step, these next two steps in one. I'm going to bring down the x and then bring it down to the denominator as 1 over x. So that's going to be the limit as x goes to infinity of the natural log of 1 minus 3 over x over 1 over x. I feel like we've done those two steps enough that we can combine them into one. And now we can use L'Hopital's rule. The denominator is going to 0. The numerator is going to 0. Is the numerator going to 0? Yeah, right, because 3 over infinity is 0. 1 minus 0 is 1. Natural log of 1 is 0. Still good to think about. So now using L'Hopital's rule, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. I always remember that the derivative of 1 over x is negative 1 over x squared. So the derivative of negative 3 over x should be positive 3 over x squared. Or you can write it out, right? The derivative of negative 3 over x is the derivative of negative 3x to the negative 1, which is 3x to the negative 2, which is 3 over x squared. Derivative of 1 over x is negative 1 over x squared. And what can I cancel out right away? The x squareds in the denominators. Especially for these ones that look like this kind of canceling happens almost all the time, where you get to cancel out the x squared like that. I'm going to simplify this as the limit as x goes to 0 of 1 over 1 minus 3 over x. And the 3 divided by negative 1 is just times a negative 3. This part goes to 0. Oh, my infinity transformed into a 0 somehow. Now that goes to 0. Otherwise, it's a problem. And then we have 1 times negative 3. So that limit's negative 3, which means the limit as x goes to infinity of 1 minus 3 over x to the x equals e to the negative 3. Questions about that one? I mean, it's very much the same as what we did before, just not exactly the same. Okay, we got a little bit of time. Let's look at, so typically the 1 to the infinity forms, which are the two we just did, always kind of turn out this way. It's typically written as 1 plus or minus some amount that's going to 0 raised to the infinity power. Actually, let's do one more because there is another kind of way of writing, which is actually a little easier. Let's say that the limit as x goes to 0 of 1 plus 2x to the 3x power, to the 3 divided by x power. This is also a 1 to the infinity form. And no, we don't have to worry about which side of 0 we're approaching. It's okay for the power up here to be a positive or a negative infinity. It works out either way. Really, well, I didn't need to get too into it. So this one, again, we're going to do this. I mean, it's always like I know it's a little bit, but for always for these exponential ones, it's always the same thing. You're always taking the natural log of the stuff, taking the limit of that, and saying your answer is e to whatever your answer is. Or the other way where you're doing e to the natural log. Let's do the e to the natural log way. That's going to be the limit as x goes to 0 of e to the natural log of all of your stuff. And then we can bring, you don't have to bring the limit up to the exponent. It feels more correct to do so, but it's not really required. We can write this as e to the limit as x goes to 0. I'm going to bring that power down. So I'm going to have 3 over x times the natural log of 1 plus 2x. Now, here's the thing about this. You don't really need to bring the 3 over x down to the bottom as its reciprocal. You could and say that you have an x over 3 in the denominator, or you just say you kind of already have what you need. In the numerator, I have 3 times natural log of 1 plus 2x. In the denominator, I have x. So I would maybe just reimagine this as e to the limit as x goes to 0 of the fraction 3 natural log of 1 plus 2x over x. It's kind of way nicer when it's written like this. It's a lot less terrible looking when you take the derivative of the top and the derivative of the bottom using L'Hopital's rule. I can use L'Hopital's rule. I've got 0 on the bottom, I've got natural log of 1 on the top. So using L'Hopital's rule, I did the thing where I wrote the limit. So I'm just going to leave it there since I did it. Oh well, such is life. The derivative of the top is going to be 3. Before I write the derivative of the top, I should think about the fact that the derivative of the bottom is just 1. I don't really need to write a fraction here. So I'm just going to do the derivative of the top is 3 times 1 over 1 plus 2x times the derivative of 1 plus 2x, which is 2. All over 1 if you really like. All right, 2x goes to 0. And we're left with e to the 3 times 1 times 2, which is e to the 6. There's our answer. But all of these always end up being e to the something. It gets, I don't know, it seems to get repetitive. You guys are like, yeah, I've seen you do it like 10 times. It's a little repetitive. Okay, let's look at a few more examples and then we'll call it a day. Because there is one other version of this, which is the infinity to the 0 types. Which doesn't feel like it should be indeterminate, but it is. Now, here's the thing, why these 3 types are indeterminate. Actually, let's talk about that for just a second, because I always wondered, like, why aren't any other types indeterminate? Well, it's really because what happens when you take the natural log? So if you have an infinity to the 0 and you take, now you don't really need to write this down, but let's say we take the natural log of infinity to the 0, which I know looks kind of funky. Well, the 0 comes down in front, and then the 0 comes down to the bottom as 1 over 0. But that's an infinity over infinity form. So infinity to the 0 is an infinity over infinity form. And it's also true of the other 2 forms we did. If you have a 0 to the 0, we take the natural log of that, you get 0 times the natural log of 0, which is natural log of 0 over 1 over 0. And natural log of 0 goes to negative infinity, and 1 over 0 could be positive or negative infinity, depending on what side of things you're on. Finally, 1 to the infinity is a natural log of that is going to be infinity times natural log of 1, which is natural log of 1 over infinity, which is a 0 over 0 type. So that's why these 3 types, when you take the natural log of them, you can use L'Hopital's rule because they all end up being either infinity over infinity or 0 over 0. And these are kind of the only ways you can get them, right? You can only get 0 over 0 if the top is 0 and the bottom is 1 over infinity, which is going to 0. You can only get infinity over infinity if you either have a natural log of infinity, which goes to infinity, or a natural log of 0, which goes to negative infinity. And the bottom is a 1 over 0, which is going to infinity. It's kind of the only way you can get from these to those. So these are your 3 exponential indeterminate forms. Again, not super important to know that this is the y of it, but kind of interesting. I always kind of wondered and thought about, like, oh yeah, that's it. Isn't anything divided by 0 does not? Yeah, so you're right. When we divide something by 0, you're correct in saying it does not exist. We're kind of abusing the notation here and saying, well, we know that when you divide by 0, it's getting infinitely large or negative infinitely large. But that is actually worth pointing out. If someone asked you what the limit, I'm going to make this very obvious. Limit as x goes to 2 from the right of 1 over x minus 2 is, technically this limit doesn't exist. However, we know enough about it to say, well, it does not exist, but we also are aware that as x is closer and closer to 2 from the right, this function does get infinitely large. So although this limit doesn't exist, we say that the limit as x approaches 2 from the right of 1 over x minus 2 is positive infinity, because that function is getting infinitely large as x approaches 2 from the right. But infinity is not a real number, so it's also correct to say the limit doesn't exist. But if your teacher asks you this question, they definitely want you to say the limit's infinity, not that it doesn't exist, right? They're definitely looking for this answer because it's a more correct answer to the question. All right, I promise you some examples like the following. Limit as x goes to infinity of the natural log of x to the 1 over x power. Okay, which is an infinity to the 0 form. So let's do it the e to the natural log way. So this will be the limit as x goes to infinity of e to the natural log of x to the 1 over x. All right, let's bring the 1 over x down in front. So it's going to be e to the limit as x goes to infinity of that 1 over x is the power on this, so it's coming down in front of the outer natural log there. So 1 over x times the natural log of x, which we probably should just write as e to the limit as x goes to infinity of the natural log of x over x. Now, before I use L'Hopital's rule, everyone should have an idea of what this is gonna do. Natural log of x over x, and x is going to infinity. Which of those functions is growing faster? Does x grow faster, or does the natural log of x go faster? Well, think about the graph. Think about the graph of just natural log of x. Which grows faster, x or natural log of x? Definitely x. And natural log of x grows even more slowly. It looks like a flat line. It's not. It does increase as time goes on, but it looks like graphics sometimes like, are you sure this isn't a flat line? It's not, but it takes forever to get really even significantly large. So we would expect this limit to be 0 because that top function is so much slower than the bottom function. By the way, this is how L'Hopital's rule is also how you tell kind of which function grows faster over time. If you take the limit of a quotient and you use L'Hopital's rule to see which one's, what the limit is. If the limit's 0, we say, oh, the top function is smaller than the bottom function. If the limit's infinity, we say, oh, the top function is bigger than the bottom function as time goes on and on. And I think one class has like a question about comparing some functions using L'Hopital's rule. That's how you do it. Using L'Hopital's rule here, if the limit is, I always want to do that. So this is why I do it the other way usually, because I always want to write the limit out in front. I'm always like, limit, right? Limit. It's been drilled into my head that if you're doing limits, you should always write the limit before you do anything else. But here I'm writing the e to the limit as x goes to infinity of. All right. Well, so again, the derivative of the bottom is going to be 1, so I'm not even going to worry about it. I'm just going to do the derivative of the top, which is 1 over the stuff times the derivative of the stuff. And that limit is definitely 0 because 1 over infinity times 1 over infinity is certainly going to 0. So it's going to be e to the 0, which is 1. Let's change it up. Yeah, I probably have a room here. Let's do the limit as x approaches infinity of x to the 3 over natural log of x. And again, let's do it this way that I am less a fan of. Well, in fact, do I need to do L'Hopital's rule? Is this indeterminate in the way that I need it to be? Yeah, I've got infinity to the 3 over infinity is 0. I've got infinity to the 0th power. So using, well, rewriting, I'm going to rewrite this as the limit as x goes to infinity of e to the natural log of 3 over the natural log of x. Sorry, I didn't give myself enough room here. That's not what I wanted to write. Let's go to the next page. Let me rewrite it again. Apologies. Limit as x goes to infinity of x to the 3 over natural log of x is going to be the limit as x goes to infinity of e to the natural log of the whole thing, which is x to the 3 over natural log of x. That's better. Okay. Again, the whole reason for doing this is that it allows us to bring down the power. So what am I going to bring down in front of the natural log here? So what am I going to have in my numerator now? Sorry, not my numerator, in my exponents. Apologies. I know usually I just fill in the answer, but it's actually confusing as to say thing. So no. So I get e to the 3 over natural log of x times natural log of x. But I don't even need to use L'Hopital's rule here. I can just cancel the natural log of x's, which means this is e to the 3rd. I don't even need the limit. I mean, I could write the limit. The limit of a constant is just the constant. So wait, does that mean that this expression is equal to that expression? I mean, I guess it does, right? So interesting fact, e to the 3 over the natural log of x is just equal to, sorry, x to the 3 over natural log of x is just equal to e to the 3rd. Or if you drop the 3, x to the 1 over natural log of x is just equal to e. Kind of funky. If you graph this, well, it's equal to e if x is greater than 0. Right? Because you can't take the natural log of a negative number. So kind of a bizarre example. It's kind of weird to think about that this is true, but it's not important. It is true. It's kind of interesting, but it's not that important.